Um, Good evening. Yeah, could you please tell if I'm audible? Okay, so yeah, I guess we can start now. If more participants join, then we can like take them later. Yeah. So yeah, welcome to the live session for week 3 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dixit from IIT Kharagpur. And I am Anant Singhal, a PhD student from IIT Jodhpur, and I'll be assisting you in solving some of the similar assignment problems that have been given to you in the week 3 assignment. And I'll try to cover the very basic of the topic first, and then we'll go quickly see some of the problems. And yeah, so that's how we'll go. So in the initial 2 weeks, if you have already attended, then we have covered like some of the basic structures or some of the basic part, that how first of all why only silicon, and why what is device simulation, what is modeling, etc. And we also read about on the atomic level that what is the atomic structure or what are the mirror indices, etc. And we see some of the basics or more into the basics by going into this doping and the band structure part. uh, yeah, so yeah, these two were the like major important topics that we have covered till now. And I guess today is the most probably the most important lecture, because these topics that are written in this particular week, that is density of states, electron mobility, and this Fermi Dirac function and the carrier concentration. So these are the most important topics. So if you have a good basic knowledge about these topics, then you'll never be able to like you'll not fail to understand the physics part of all these devices that are coming in the upcoming weeks. So you see in the upcoming weeks we have several devices such as PN junction. One is PN junction, one is BJT. Then we have field effect transistors such as MOSFET, HEMT, etc. So if you have a clarity of these topics, then week 4, 5, 6 will be pretty easy for you. Otherwise, if you don't have that particular knowledge, then the rest of the week's topics will be very uh, it might seem very tough to understand those topics. Yeah, so I guess we can start now. So I hope you remember. So in the I guess in the last class we ended it with some Schrodinger equation, and we came out with a wave function of something like for an infinite particle, the wave function is something like sine kx n pi by l. And whereas n is some integer. So I guess this is how I ended the last previous class. And here we got to know that the electron behaves only not only as a particle but also as a wave, and this is the wave function, that is what we use to denote it, or that is how we use to capture the transport of an electron from one place to another. So now there are some physical terms that are associated with electrons. So till now we have not talked about any external bias or anything, but we were only like majorly interested on the structure part, mainly focusing on the doping, how the doping changes the Fermi level, or not even the Fermi level, but the band diagram, etc. So, today we'll go into some of the basics to cover the particular topics such as density of states, carrier concentration, etc. So, I'd like to start with first of all electric field intensity. I hope you have already seen the videos for this particular course also. That will further help you in understanding the basics really well. So what is electric field intensity? So electric field intensity is nothing but, let us consider as a semiconductor bar, let's say, which is having some certain length L, and let's say this is x equals to 0 and this is x equals to L. And what I am doing is I am applying a certain voltage across it. Let's say that voltage is V. So electric field intensity is nothing but, it is the change in the voltage with respect to the position of the semiconductor bar. So for this particular case, let's say I want to talk about the corners. So the change in the velocity is minus, sorry, not velocity, the voltage is, let's say at 0 it is 0, at L it is V. As I said, at 0 it is 0, at L it is V. So this will come out to be V by L, right? So electric field is always first of all, it is always directed towards high voltage to low voltage. So here you see there is a positive bias. So let's say here there is a voltage V and here it is 0. So the direction of electric field will always be like this, from a higher voltage to a lower voltage. And we know that by applying any voltage, we do exert a force which is nothing but F is nothing but Q into E. So this is the electric field which is exerting a force on the electrons, because let's say I have applied some positive bias. So let's say there is electron, so it will get attracted towards this positive bias, right? The positive, let's say the proton gets attracted towards the electron. It is like that only. So for electrons, we know that the charge is negative. So what I can write, let's say I'm denoting it as minus QE because of the negative charge. Hence the force experienced by the electrons is opposite to the direction of electric field. So you see, let's say this is the voltage. As I said, the electric field is in the direction of high potential to low potential. So the force related to the electron will be like this. And similarly, the for the holes. So this is for electrons. If I write for the holes, we know for holes it is plus QE because of positive charge. So let me write here electrons, let me write here holes. So here what we'll see is, again, if the electric field is from a higher voltage to lower voltage, then the holes will also see a force from higher voltage to a lower voltage. Like the electric field and the direction or the force will be exerted in a same direction. So this is a very basic of what is electric field, like in a very layman term. So why electric field is because we are very worried about this thing, which is velocity of carriers. This has a huge impact on the any device, because what we want is at the end we want more and more current through any semiconductor device. We are trying to control that current. So that current is nothing but the flow of charge. So if we can somehow like deduct what is the velocity of carriers, or we can somehow increase the velocity, there will be more and more current. So we need to have a certain knowledge. So the velocity basically can be due to two things. The electron can have a thermal velocity. So as the name suggests, thermal. So why it is the thermal? It will be due to temperature. So there will be some temperature changes once you apply some voltage due to some heat. So that will create the thermal velocity. Then there is a very important term which you might have heard, is the drift velocity. So this is velocity which is due to the application of electric field. So if I talk very briefly about thermal velocity, this is very straightforward. I guess you already know about it. That we know that let us suppose we have a semiconductor material which is kept at the temperature T, and there is no electric field applied. Again, so thermal velocity will be there without even any electric field. So in this case, we know that the electron will have any energy, which is, let's say I'm denoting energy as something like this, which is 3 by 2 kT, right? This is the Boltzmann law that we know. So where k is a Boltzmann constant, and this will be nothing but the half mv square the energy. If I write, it will be 3 by 2 kT. So now this velocity, if I try to calculate, let's say I'm denoting it at th because thermal. So it will be nothing but under root 3 kT by m, right? So this is nothing but the thermal velocity. So here we know that K is 1.38 times 10 raised by minus 23 joule per Kelvin. So these are all Boltzmann constant and other things. So if you try to calculate it at room temperature, let's say I'm keeping T as 300 Kelvin, and if you put everything, because we know what is K, what is T, and what is the mass of an electron, let's say absolute mass, which is nothing but 9.1 10 raised by minus 31. So if you put it, it will come out to be around 10 raised per 5 meter per second, or I can write the same as 10 raised per 7 centimeter per second. So what I can say is, at room temperature, the thermal velocity of electron is 10 raised per 7 centimeter per second. I hope this is very clear, and the electron in a semiconductor are therefore moving rapidly. I mean, you see this velocity is quite high. I mean, you might know that the speed of light, which is very high, it is around 3.8 10 raised per 13, sorry, 3 into 10 raised per 8 meter per second. It is quite close to this. I mean, there is some order difference, but yeah, it is very high. So electrons, we know now that they are moving very rapidly now. So the thermal motion of individual electron may be visualized as a succession of random scattering. So let's say electron was here, so it can go here, then it can go from here to here, it can go from here, something like that, and it can even come up back from where it has started. So the random motion of this electron leads to a zero net displacement. So since we are not applying any force, so it will come back and it will be a zero net displacement. And let's say a electron was there, so uh, the time that we define to collide in between these is, it is known as the collision time, which is denoted by tau c. which is the average collision time. So like this is a very basic about the thermal velocity. So what we have understood till now, that the electron cannot go beyond this velocity because this is the maximum thermal velocity. I mean, if we change the temperature, then yes it can, but if we talk about room temperature, that we'll be talking about always about room temperature only. So if the electron achieves this velocity, then there is no external force that can increase this velocity further. So that is one case. Then there is a case for drift velocity. So can anyone tell what is the reason of drift velocity? I just told why this drift velocity comes into the picture.
Due to electric field.
Yes, so that is good, due to electric field. So as she said that this is due to electric field. So let's say this is some semiconductor which is having some atoms, or let's say these are silicon atoms. So now let's say I apply a certain electric field. Maybe I can make a similar picture as I made before. So we know that the electric field will be like this, from higher voltage to lower voltage, right? So electron are moving like this and the hole are moving like this. So this is what we see. So let's say now I applied a electric field here. So what will happen? The electron, let's say there is an electron here present. So it will move in some way. Let's say it is moving like this. So it will go from here, it will go from here, let's say. So there is a possibility that there might be a collision of this electron with this particular atom. Or what else is, there is a thermal, as I said, the device or the substrate may get heated up, which will result in the movement of these particles. Like you should have read about this. This is nothing but scattering. So, or I can write in English, it is ziggling. So if the particles are moving like up and down, so there is a huge possibility that the electron is getting somehow colliding with these particles and all. So this is having a definitely having an impact on this. So on the application of this electric field, electron will start to move in the opposite direction first of all of the electric field, as I said. So electric field, if it is like this, so electron are moving like this, and this movement of electron under the influence of this electric field is known as the drift. So now let's say we have an electron in vacuum. Let me ask you a very simple question. Let's say we have an electron in vacuum. Uh, so as soon as we are applying an electric field, this electron will experience a force, right? And that force will be something equals to F is equals to m. If I talk in very basic terms, let's say Newton's second law. So if I again, if I'm asking that if we have an electron in vacuum and we apply a certain electric field, so there will be some force, right? So now the movement of this electron, is it as simple for the case of a crystal as for a vacuum? So what you can see, once I apply a force, or sorry, once I applied the electric field for a case in vacuum, the electron velocity will accelerate, right? There is a certain acceleration involved due to the application of force. But what happens in a complex structure is, as I said, there can be some scattering, there can be some collisions, etc. So if we, let's say if we talk about, if there is an electric field, the electron almost never goes through semiconductor without interacting with these atoms. And all these atoms are also vibrating. So these are the two main effects. So these vibrations are first of all due to thermal energy, as I said. And these all effects, by like colliding and all the thermal vibration, they result in a very strong interaction of free electrons and holes to the scattering of free electrons, right? So electron, they are trying to accelerate, right? If I talk in terms of vacuum, but every time they are colliding, they are losing some of the velocity because of the collision or because of the vibrations. So they are trying to accelerate, they are coming into rest because of some collision, they are again trying to accelerate, they are coming into collision, and something like that. So it is happening periodically such that the electron never achieves a acceleration, but it moves with a constant velocity. So are you trying to understand what I'm trying to say? Do you understand that there is a collision, so they cannot accelerate, they will come to some time to rest, and then they'll again try to accelerate. Due to this constant collision, the average acceleration is zero. I mean, it is going through a constant velocity. Again, I'm asking, so are you able to understand this?
Yes, yes.
Yeah, so this constant velocity is what we call as drift velocity. Yeah. So now as you see, so this drift velocity of an electron is due to electric field. So this is a very purely linear function of electron, and if I write in some constant terms, so it is dependent upon the mobility of electron, and here the relation comes out to be Vd, which is the drift velocity as a function of mobility and electric field. So again, if I talk about mathematically, so let's say I'm talking about electrons as of now. So this is mobility of electrons, which is denoted by mu n. Okay, I'm not writing it. So it can be for holes also, which is mu p. So this is mobility for electron and holes. Similarly, E is the electric field. We all already know about that. And so mobility is, if you want to define it, is nothing but Vd by E, right? So it can be defined as a drift velocity per unit applied electric field. So I mean, you can remember few values because we'll be dealing with certain numericals. So for silicon, the electron mobility comes around 1300 centimeter square per volt second. You also should be good about the units because that helps in a certain lot of calculations that will help you in learning the formulas quicker, etc. And the velocity, sorry, the mobility of silicon for holes is centimeter square, 500 centimeter square per volt second. So if I now try to make Vd as a function of electric field, so Vd is equals to mu E. So how do you think this plot will look like? Anyone, any guesses?
Yeah, with the increase in electric field, the drift velocity will increase.
Yes,
I mean,
it's
it will be linearly initially, and it will reach to saturation.
okay. So like this.
Yeah, something. Yeah,
Yeah. So can you tell why this saturation happened here? Since you have already told that it will look like this and this is correct. So you see there is a linear relation here. So Vd should increase with electric field, but there is some saturation happening. So again the question is why? I have just explained. I mean I have given a very basic knowledge about it. Any idea, anyone?
so it's a maximum velocity with which electron can move.
Yes. So as I said that this drift velocity cannot go beyond this thermal velocity. So there is a specific range or even there is a specific around electric field value. So if it is around 10 to the power 3 to 4 in volt per centimeter, and this is again centimeter per second. So if I say for the previous case this value is around 10 raised per 7 centimeter per second. So it will never go beyond that. It will saturate after a certain application of electric field. So what it means is you apply any kind of force after this, it will never increase the velocity. So this is what you call as velocity saturation also. So I hope it is clear. I mean, this is quite basic, but yeah, these are all the interesting things that is happening. So what I can say that for a smaller electric field, like this case, sorry, let me change the color. So for this case, for smaller electric field, what we have is this mobility remains constant, and due to which the Vd has a perfectly linear relationship with E, because this mobility remains constant. But once I go towards, let's say, a larger electric field, maybe here. So what happens? The mobility starts to decrease because we have a certain restraint now. So once this thing decreases, now to keep, even if we are applying more and more electric field, because this is decreasing, this is making it constant. So that is why this plot looks like this. Is it clear?
yes.
Yeah. So I mean, I have already discussed the concept of phonon scattering in the previous classes, that there is this lightest vibration that can again cause some of the scattering. So this is because this is due to the phonon. So that is why this is known as phonon scattering. So I'm not going much into that. So maybe what we can do is we can, do we have problems for scattering? Give me a minute. Yeah. So I guess we already have few. So this is, I guess, already done in the previous class. Yeah. So here you see the problem is the dependence of drift velocity on electric field for N-type semiconductor is shown. The N-type silicon with majority carrier concentration is based in 1 volt voltage source, sorry, is biased with 1 volt source across the length of semiconductor 1 micron. You need to calculate the drift velocity. So can you do that? I mean, do you want to try it by yourself?
Yeah, well, we'll try.
Sure, sure. So maybe everyone you try to take 2 to 3 minutes. If you are able to get any answer, please type in the chat box and then I'll also solve. Any answers? So let me give you one clarity here that this axis is 10 raised per 5 volt per centimeter. That means this value is 10 raised per 5 volt per centimeter, and this is 10 raised per 7. And on the x-axis, this is, or the velocity that we have, it is 0. This is 10 raised per 7. This value is 1, and yeah. Any idea? Okay.
We'll get electric field value, then E is equal to L by like V by T by L.
Yeah.
So that will
Okay.
get 10 power 6.
Okay, so let me do it. No problem. So we have a L of 1 micron, which is 10, 1 raised per 10 raised per minus 4 centimeter. So I can write minus 4 volt per centimeter. So electric field will come out to be 10 raised per 4 volt per centimeter. And Vd is nothing but, as I just said, mu e. So mu is nothing but the slope of this, right? So slope we can calculate directly. So pi 2 minus,
Micro 10 power 6, right? Minus 6.
where?
Like 1 micro.
Hmm.
Yeah. So it's okay,
So
centimeter here.
centimeter. Yeah, yeah.
Okay,
So
okay, okay, okay. Units are
options,
important,
yes,
yeah.
yes. Yeah, so it is generally in centimeter. You always change it in centimeter. So now the slope is y2 minus y1 is 10 raised to power 7 minus 0, and at the same time x is 10 raised to power minus 5 by 0. So mobility is nothing but 100 centimeter square per volt second. So Vd is nothing but 100 times of electric field, which is 10 raised to power 6 centimeter per second. Uh, there is no option like that, kya? Oh yeah, there is. So option D is the correct answer. This was very straightforward. I mean, I hope you are able to understand it. Is there any confusion? Okay, let me maybe give you a very simple problem
Can
then.
you
Yes,
reiterate that when 10 power 7 minus 0, this is the mu value which you are
yes,
calculating?
yes. So this is the slope of this line. I mean, slope
Okay.
is nothing but, I mean, in general mathematics, it is y2 minus y1 by x2 minus x1, right? So y2 is this point, which is 10 is per 7, and y1 is 0.
Okay. From there, you got the mu value and
Yes, yes.
multiplied it. Okay. Okay. Okay.
Yeah.
Thanks.
Yes. Let me give you a simpler problem. I guess there is some confusion. So let's say we have a DC voltage of 10 volt across an n-type silicon bar. So I'm now defining silicon. So that means the mu will be, uh, let's say you are taking it 1000 centimeter square per volt second. I'm giving you mu directly. And the length of the silicon bar is, let's say, 1 centimeter. Now the donor doping concentration, let's say ND, which we talked about what is donor and what is acceptor, uh, and the mobility is, I mean, the donor concentration is, let's say, 10 is per 16 per centimeter cube. Uh, so yeah, so what you need to do is you need to find the average time taken by the electron from to move from one end to another. So average time, by time I mean time is nothing but, I mean, this is very straightforward, distance upon speed. So you need to calculate the drift velocity, and you already know the distance, so you'll be able to calculate the time. Is the question clear? Any
Yes.
Yeah, so quickly do it. I mean, that will make it better. Any answer?
Is it 10 per minus 4 seconds?
Okay, so I mean, let me try quickly. This is pretty straightforward. So L is 1 centimeter. So I'm keeping everything in centimeter. VD is mu E. So mu is 1000. E is nothing but 10 volt by L. L is 1 centimeter. So it is 10. So yeah, centimeter will get cancelled. So it is 10 is power minus 4. Yeah. Or you can write this as 100 microseconds. Yeah, so this is fine, I guess. Okay. We have the same problem, I guess, again, or it's different. Yeah, it is different. So now we have again the same plot. The values are same. It is biased with the same thing and same length. So what you need to do is you need to calculate the current density due to majority charge carrier. So I hope you are already aware about the concept of current density. Current density is nothing but, you might have seen this relation NQ mu. Uh, so since this is n type, this will be mu n, and I mean, this comes from here. The current, we know that it is NEA VD, and VD is nothing but mu E. So NEA mu E. So if I write I by A, this is the density. So NE, what do are we left with? Mu E. Yeah, so NQ mu, you see, is the current. I have written something wrong or what? This is sigma E. J is equals to sigma E. So this is sigma. I mean, this is the Ohm's law. So yeah, that is what it is. NQ mu E. Oh yeah, I left E here. And this part is the conductivity, sigma. I guess you need to calculate what current density. Yeah. Do you want to try this? Please let me know if you want to try.
So when when the concentration of P is not given, so we take it as zero, right? I mean,
Yeah.
because the conductivity is from both N and P.
Yes. So let me give you a very basic example. So let's say we have a N-type semiconductor which is n² per centimeter cube, and we know that Np is an I square. Give me a moment. We know Np is an I square, so Ni is in general 10^10 order, right? So if I try to calculate P from here at equilibrium, it is 10^20 by 17, which is only 1000. So 1000 is negligible as compared to 10^17. So the exact formula, if I try to write, this is nothing but NQ mu N plus PQ mu P times E. So this term becomes 0 or negligible as compared to this. So that is why I write this directly. Yeah. So again, so are you trying to calculate it or I'll do it?
We'll try once.
Sure, sure. Any answer? Okay, so let me try it because this is again straightforward. So we need to find the current density, which is sigma E, or I can write this as NQ mu E. So N is nothing but the electron concentration, which is given. Yes, any answer? 10 is for 13. Got one is C. So let's see. Uh, we know the charge is 1.6, 10 is for minus 19. Mobility we have just calculated is 1000, I guess, or 100. What was that? Mobility 100. Okay, mobility is 100 and electric field is V by L. So that is also we calculated, it is 10 is power 4, I guess. So this is 10 is power 7, this is 20.
The mu term 10 power 7 divided by 10 power 5, right? So it should be 10
Yeah,
power 2 here.
it is 100.
Yeah.
So this is 6 and 19. Yeah, so it will go away. So the answer will be 1.6 ampere per centimeter square. So again, I'll like to say that keep everything in centimeter for these numericals because that will help you solve quicker. So it is 1.6 ampere per centimeter square. Option C is correct. Is it fine? Any doubts? If not, then try to do this problem. So the problem states you need to find the conductivity. So conductivity is this sigma term. And if I try to write completely, it is P mu P Q, sorry, N Q mu N. I mean, to simplify, I'm writing like this, P Q mu P. So this thing is conductivity, which is also 1 by resistivity. But yeah, for this problem, you need to find the conductivity of semiconductor doped with this pentavalent impurities, and mu N or mu P, and Ni is given. Any doubts in this problem? First of all, let me know that if you have doubts. Then anyone having any doubts in this? Okay, so I'm considering that you will be able to solve it and you are trying it, right?
Yeah, we are trying.
Okay. Okay. So anyone wants to explain the approach that they have followed? Anyone? Okay, so let me do it. So first of all, it says that the semiconductor is doped with pentavalent impurity. So what does it mean? Is it N type or P type?
Enter.
Yeah. So N type means yes.
Yeah, yeah, enter.
Yeah. N type means ND is 10 is for 16. So now again, if I now try to calculate P, which is Ni square by ND. it will come 10 to the power 4, which is negligible. So what I can do is I can neglect this term. So it is nothing but sigma is nq mu n. So this was very easy, I guess. N is nd, which is 10 to the power 16. Mu is 1.6 minus 19. And mu n, is it given? It is given. It is 1800. So this is 181.8 times this. So it will come around 1.6 times 1.8, which is 16144. 44 plus 32 is 1.76, right?
2.88. Yeah.
Okay, 2.88.
Yeah.
So what will be the unit? Conductivity. It is opposite of resistivity.
Simon.
Sorry?
Simon.
Yeah. Oh, resistivity is Ra by L, right? So this is ohm meter. So conductivity will be Simon per centimeter. Make sense?
Mm-hmm.
Yeah. So yeah. So before going into further problems, let me try to introduce you with the next important topic, which is Fermi-Dirac distribution function. So can anyone tell what is this Fermi-Dirac distribution function? Any basic idea? I mean, any guesses?
Probability of an electron sitting in density of state in any of the states.
Okay, yeah, something like that. Yeah, so that is almost correct. So Fermi-Dirac distribution functions give you the probability of an electron at a particular energy level and at a particular temperature. So let me define. So as we already discussed that previously, that the particles follow the Pauli's exclusion principle. So we have a certain probability of electron associated, which is the Fermi-Dirac distribution function, which is given by 1 upon exponential E minus EF over KT, where EF is the Fermi energy level, K is the Boltzmann constant, and T is the temperature. So if I now try to define Fe, so as she said, that it is nothing but the probability of an electron, or probability of finding an electron, I can write, at energy level E and at temperature T. So this is energy level and this is temperature, and this is in Kelvin. So can someone now tell what is 1 minus Fe?
Probability of finding holes.
Yeah, that is correct. So we know that since the total probability is 1, so 1 minus Fe will be the rest of the remaining holes. And again, EF is the Fermi level, T is the temperature, and K is the Boltzmann constant. So if we like try to go in very basic of this, so let's say at T, maybe this is the first thing, at T which is not equals to 0 Kelvin and E is equals to EF. So can we if we try to calculate Fermi direct, so what it will come? So this is nothing but 1 upon 1 minus exponential of 0 over KT. So what will be the answer? Sorry, this is plus.
Fi- Uh, 1/2.
Yeah, 1 by 2. So what we can say is Fermi level is that energy level at which the probability of finding an electron is,
Equal to probability of finding holes.
yeah, or it is 1 by 2. Yeah, so that is the basic definition, that the Fermi level is that energy level at which the probability of finding an electron is 1 by 2. And now if I try to take second guess, let's say I'm talking about 0 Kelvin now. And the first case I'm considering inside this is at E greater than EF. So what I can write is Fe. 1 upon 1 plus exponential E minus EF over KT is the formula. So what will be FE at t is equals to 0 and when E is greater than EF? Any idea? Come on, this is basic maths. I'm hoping this answer from you guys only. So if t is 0, what will be this term? Sorry, I did not hear.
We require minus infinity.
If t is 0, then this will be minus infinity. E is greater than EF, I'm saying.
Okay, okay. Yes. Yeah, 0 with e to the power of infinity.
Yeah, it will be infinity, right? And e to the power infinity is
E to the power infinity is 0. Is it? I am not sure.
E, the value of E is 2.7 something. So is to the power infinity is infinity.
Infinity.
So 1 by infinity is always 0.
Yeah, e to the power minus infinity is 0. Okay.
Yeah, e to the minus infinity, sorry, e to the minus, it is 0. Yes.
Okay.
So this comes to the next case. So let's say now if I'm taking if E is less than EF, so what will be FE? It is 1 upon 1 plus e raised by minus infinity. So what will be this?
1.
Yeah. So now here what we can say is, let's say this is for the Fermi level. So the probability of finding the electron below the Fermi level at t is equals to 0 is always 1, and the probability of finding the electron above the Fermi level at t is equals to 0 is always 0. So what it is saying that at t is equals to 0 it is always empty and this is always filled. Make sense? Any idea? Oh, sorry, any doubt in this?
Yeah. But mathematically, we understood, but I mean, how did this concept arrive? Okay, it is related to the
Yeah.
math itself, or
No, no,
how?
no. I did explain the physics behind it in the previous lecture. I mean,
Uh,
uh, the valence and the conduction band. Did you see that lecture? I mean,
uh,
what were we saying that the probability or the movement of electron in the valence band is always nothing, right? The electron only becomes free when it is goes from the valence to conduction band. All the electrons are contained by valence band, or even we prove that at 0 Kelvin the semiconductor behave like a pure insulator, right?
hmm,
So
yeah,
valence band
yeah,
is,
because of the thermal energy. I mean,
yeah,
okay.
yeah. So the valence band is always filled and the conduction band is always empty. That is what it is mean to say.
Yeah, as the temperature increases, the thermal, I mean, the electron gets excited and they move to the
Yes, yes,
conduction band. Yeah, okay. Then the
yeah,
probability increases.
yeah. So it will start increasing, and this will start decreasing, something like that. So yeah, let me give a pictorial view that will clear your doubt, I guess. So let's say this is EF, sorry, and this is, let's say, Fermi function. So what I just made is, let's say this is 1 and this is EF. Let's say this point, and this is E, let's say not EF. So it is 0, right? So this particular thing, you see that at E less than EF, the probability of finding an electron is always 1, and at after that the probability is always 0, right? if
Yes.
if the temperature comes into the picture now, so what tends to happen is this will go something like this. Make sense? Any doubt in this? Anyone, any doubts? So this is
Okay.
okay. So yeah, this is, yeah. So if I try to summarize in some important points, so First of all, Fermi Fe is the probability. It is not, yeah, it is the probability of finding an electron at particular energy level E. Then EF is the Fermi energy level. At any temperature, the probability of finding an electron at EF is always 0.5. So this is what we have established, that if I talk about any temperature, the probability of finding any electron at EF is always 0.5. And further is the probability that an electron occupies a state at an energy level is Fe. Hence the probability of electron, or sorry, hole occupying that state is 1 minus Fe. I mean, this is just to summarize this. Make sense? Any doubts in this?
Yep.
Okay, okay.
Even when
So,
the temperature raises,
okay, yeah, that is a good thing. So yeah, that is a good point. So you have already asked. So what do you think if, let's say, this thing is T1, for instance, and this is not equal to 0. Let's say a temperature T2 comes which is greater than that of T1. So what will happen? So what will happen is, I mean, I'll tell, it will go more far away from this, and again it will go more far away from this. Make sense? So this is T2.
yeah, yeah,
Yeah.
correct. Because more electrons will move from valence to
Yes,
conduction
yes, yes.
because of thermally
Yeah. So
thermal.
this will always go away from 1. I mean, this will always lower down because the electrons are moving from valence to conduction band by more and more temperature. So here comes one more thing, that now we know that if E minus EF is very, very greater than KT, I mean, you all have already heard about this Boltzmann approximation. So if it is not there, let me clarify this also. This problem. So let's say if E minus EF is greater than KT, that means greater than, by that I mean if it is greater than 3 KT, that is enough to create the difference. So this Fe that we have Fermi Dirac, what we do is 1 upon exponential E minus EF over KT, right? This is the actual Fe. But this is, if this is very, very greater than this KT. So what happens is this term becomes very high as compared to this one. So what we do is we just write this as 1 upon exponential of E minus EF over KT, which gives this as exponential of minus EF minus EI over KT. Sorry, EF, E minus EF. Sorry. So this will be minus E minus EF over KT. Makes sense to everyone? This is what we call as Boltzmann approximation. And the same is when it is very, very less than. So E minus EF, if it is very, very less than KT, so these terms then become more prominent to the holes. So if I now try to calculate the hole concentration, sorry, the probability of holes, which is 1 minus Fe. So what I can write is 1 minus 1 upon 1 plus exponential of the same thing, E minus EF or KT. So again, if I try to simplify it, it will be exponential of E minus EF over KT upon 1 plus this term again. I'm writing is like this. And since this is very less as compared to 1, the denominator term, so it will be 1 minus Fe will be exponential of E minus EF over KT. Make sense? Any doubts here? Please let me know right now only. Okay. So you can,
Yeah.
yeah, okay. So let me try to give you a problem that will, I mean, clear your understanding more. So let's say the Fermi level, energy level of a silicon material. Sorry, question. Let's say the Fermi level is at 5.5 electron volt. The electron in this material follow the Fermi Dirac distribution function you need to determine the temperature at which, now try to understand the question clearly, at which temperature at which the probability at which there is a probability, let's say there is a probability of 2% that a state 0.25 electron volt below the Fermi level of an electron. So try to understand the problem. So the electron in this material follow the Fermi Dirac. First of all, you need to determine the temperature at which there is a probability of 2% that a state 0.25 below the Fermi level will empty an electron. Will be empty. Sorry, I forgot to write will be empty. Will be empty. Empty is a keyword of an electron. Are you able to understand the question? If not, please let me know. I'll do it. So we have a Fermi level at 5.5 electron volt. We need to find the temperature where there is a probability of 2% only that the state 0.25 below the Fermi level, 0.25 below this, 0.25 below the Fermi level will be empty of an electron. So can anyone tell what is this 2%?
I mean, electron, I mean, point two. Fermi direct. F of E.
Will be empty of an electron.
Below the Fermi level will be an empty of an electron. So, okay.
If I write filled,
Fine. Fe, okay then.
so I've
Field,
written empty. Yeah,
yeah, 1 minus F. So it's 98.
yeah. So it is 1 minus Fe. No. So it is saying that 2% is will be empty of an electron. So 1 minus Fe is 2%. That is what it mean to say, right? And again, so this energy level is, let's say this is E, is 0.25 electron below the Fermi level. So this is minus 0.25. Are these two lines clear to everyone? If not, please let me know.
Can you explain once again?
Okay.
The
So
concept of Fermi level will be empty and fit.
yes. So let's say I have complicated the problem, but let's say the probability, if it says that the probability of 2% that the state, let's forget these four words for now, right? Let's forget these words. So it is saying that probability of a 2% that a state will be occupied, let's say if it is, let's say even forget this. So if it is saying 2% that a state will be occupied of an electron, so what you will say that Fe is 2%, right?
Yes. Yeah.
Now it is saying that it is empty. So first of all, 1 minus Fe it is saying, and it is 2%. And the second
Mm.
thing that it is saying that this state is 0.25 electron volt below the Fermi level. So if I, let's say this state is E1, not even E. So E1 minus EF is, since this state is below, so this is E1, sorry, and this is EF. So this is 0.25 electron volt below. So E1 minus EF will be minus 0.25, right? Any
Mm.
doubts?
Yeah, got it.
Yeah, so you need to now compute the temperature. So can you do it? Please let me know if you are trying. Let me solve it side by side, I guess. So I have already established that 1 minus Fe1 is 2%, that is 0.02. So 1 minus Fe1 is nothing but 1 upon 1 plus exponential E1 minus EF over KT is 0.02. So what I can write is, if I take the LCM and all, it will be exponential of E1 minus EF over KT upon 1 plus exponential of E1 minus EF over KT. This is nothing but 0.02, right? Or I can write in simplification, if I try to divide both numerator and denominator by this term, so it will be 1 upon 1 plus exponential of minus E1 minus EF over KT. This is nothing but 2 by 100. Any doubts still here? Okay. So this term with minus, this is 0.25 I've given. So this is 1 upon 1 plus exponential of 0.25 by KT is 2 by 100. And K we know that, so since this is in electron volt, so K is, I mean, I wrote it is this value in joule, which is joule per Kelvin. The same in electron volts. If we divide it by 10, 1.6 into 10 is power minus 19, this is 8.62 10 is power minus 5 electron volt per Kelvin. So if you divide joule by the charge, it converts into electron volt. So we have all the values. We just need to find T. So let me do it. I mean, 0.25 exponential of 0.25 over KT. So this goes here, let's say 2 times of this, 50 minus 1, so this will be 49. Now if I try to take log of both the sides, so this will be 0.25 by KT, and this is ln 49. T will be nothing but 0.25 divided by K into ln 49. K is 8.62 into 10 to the minus 5 and ln 49. This will be the temperature in Kelvin. Please let me know if you have understood this. This is quite important, I mean. Any doubts here? Any doubts? So if you solve it, this will come out to be 745.2 Kelvin. So now, I mean, there is a huge derivation of density of states and carrier concentration and all. So let me not deep dive into it, and let me give you the direct formulas that we have already established in the video lecture. So we have, we can find the electron concentration. So there are two things. So this is EC, this is EV, and this is EI, which is the intrinsic level. So let's say if I talk about an n-type semiconductor, so we know now, like we have established this, that the Fermi level is close to the conduction band. So now there are two things here. One is EF minus EC and one is EF minus EI. So we can calculate based upon these differences the value of the concentration. So the first formula is, if I talk about in terms of the effective density of states, which is NC, this is exponential of minus EC minus EF over KT. The second is nothing but N is Ni exponential of EF minus EI over KT. So how can you remember this? It is very easy. So can anyone tell if Ni is greater or than or lower of N, if it is an N-type semiconductor? Is this greater or this?
N will be greater.
Yeah, N will be greater, right? So this exponential term should be positive. So that means EF minus EF should be there in the bracket, right? Because EF is above EI. So that is one way to, what to say, one way to remember this. And similarly, it goes for a p-type also. So for a p-type, the Fermi level is close to the valence band. Let's say this is EV, this is EC, and this is EI. Now there are again two things. So again, P is NV. So this is the effective density of states for the valence band, exponential of EF minus EV over KT. And P is also Ni exponential of EI minus EF for KT. So again, because EI is above than that of EF for a P type. So these four formulas can solve any concentration numerical. I mean, is there any doubt in these formulas? I can explain right now. Otherwise, we can move ahead using these formulas. Any doubts? Anyone?
What is NC representing?
NC is the effective density of states. So, I mean, density of states is the. Have you read about the density of states? So,
No,
DOS is no. So, like, there is no video lecture of this. I mean, this has already not happened in the course.
I covered today this week.
Acha, acha, you have not covered. Oh, that is the case. So density of states is a number of solutions. So we do now know that there are a number of particular states that are the solution of the Schrodinger. So density of states represent the number of solution or the number of states per unit energy per unit volume. So if we try to, I mean, if we try to derive that, so we got to know that density of states is a square root function of this energy, and this energy now has a certain lot of constant terms, which is one of the constant is NC. Now this is again a lot, I mean it is complex, you need to see the derivation for that, but this is one of the constants that is a function of both temperature and the doping. So this is what we call as effective density of states for conduction band, and this is what we call as effective density of states for valence band. I mean the range is around 10 is per 19 for this, and this also the range of Ni is around 10 is per 10, and the N is always less than NC. I mean, not always. For the non-degenerate semiconductor that we talk about, I mean, when the Fermi level is below the conduction band. And yeah, again, so for N and P, the range is around, I mean, we all know this is 15 to 70. Make sense? I mean, for the NC and V, you need to see the derivation also. If you have any problem in the derivation, you can let me know in the next class. I will derive that. There is no problem in that.
Okay, okay.
Yeah.
Thank you.
So yeah, these are the four formulas. I mean, you can solve any problem, I guess. Do I have any problem in that? Let me check. Sorry. So let's say this is one problem. So what the problem states that calculate the shift in intrinsic Fermi level when the semiconductor is doped with pentavalent impurity of this. Assume KT this and Ni this. So shift in the intrinsic Fermi level. So can anyone tell what do we need to calculate here? Anyone? Okay, let me frame it differently. So what we have is pentavalent impurity. So what kind of semiconductor do we have?
Uh,
N-type.
Yeah,
type.
so we have N type. You all are saying. So the band diagram for N type should be looking something like this. This is EF. So now the question is saying calculate the shift in intrinsic Fermi level when the semiconductor is doped with this. Assume this. So what do we need to calculate?
EI minus EF.
Yes, exactly. So since we need to calculate in positive terms, so I'm writing EF minus EI, let's say. So we need to calculate EF minus EI. So what do you think, which formula can we use?
The second one in N-type. Yep.
Yeah. So do you want to try it, everyone? Okay. It seems a no or a yes. I don't know.
Yeah, I will drive it.
Okay.
300 milli electron volt.
Okay.
Oh, wait, 0.3. Yeah.
Yeah, so let's see. Let me try to solve it also. This is quite straightforward वैसे. So we know n is
3 electron volt.
yeah. Okay, so two of them have same answer now, so it should be correct then. So this is 10 to the 15 10 to the 10 exponential of EF minus EI over KT. KT is 26 milli, so it will be nothing but 10 to the 5. So EF minus EI. So you always try to take the log of everything, so that makes things easier. So if you try to calculate now, it is nothing but 26 milli electron volt ln 5. Sorry, ln 10 to the 5. So this is coming out to be 0.3. Please let me know if it is.
I got this answer.
Sorry.
I got this the same answer.
Okay, so I'm not calculating. I mean, since two of you have got the same, so the correct answer will be option A. Okay. So yeah, so here we have to this. Okay. Determine the ratio of intensity. Blah, blah, blah. Okay. I need to explain one thing before this to solve this problem. So now what you see is n is ni exponential of EF minus EI over KT, right? And you also see P as ni exponential of EI minus EF over KT. So we know at equilibrium, what do we have? We have NP is equals to Ni square, right? Okay, let me not confuse you all. So this will get confusion. So so NC exponential of minus EC minus EF over KT, and this is NV EF minus EV over KT. Is there any doubt in these three things?
No.
Yeah, so I'm just putting the value of N and P here, right? So it will be NC NV and then exponential of KT. So exponential of A into exponential of B is what? Exponential of,
A plus B.
yes, A plus B. So I'm writing that. So this plus this will be that. So it is minus EC plus EF. What is that? I've written something wrong, I guess. C minus EC plus. Oh, sorry. This is EV minus EF. Plus EV minus EF. This is NI square. Any doubts in this?
No.
No.
EF will get cancelled out, right? And what we are left with is EV minus EC over KT. This is this, this is this. So what is EV minus EC or EC minus EV, let's say?
Band gap.
Yes,
Yep.
exactly. So EC and EV, and the difference between these things is the band gap. So what I can write is Ni square, let's say I'm writing is this. It is nothing but NC NV exponential of, so since this is EV minus EVF, so this will be exponential of minus EG over KT, right? So also I can write Ni as under root NC NV exponential of, so since this is under root, so it will be 1 by 2 extra, so 2 KT. Any doubt in this particular
No.
solution? Okay, so that is great. So now you can try to do this. So we have two semiconductor materials A and B having identical band structure except for their band gaps. Material A has a band gap of this, B has a band gap of this. Determine the ratio of their intrinsic carrier concentration. I mean, this is very easy now, but yeah, do it. Let me know the answer. Maybe you can take 2-3 minutes. That is fine. I've already got one answer is D. So let's see. I mean, this is straightforward now. So Ni, let's say I'm saying A and Nib is what we need to calculate. Since they have identical band structure or band energy, so this will cancel out. The only difference is, what is the only difference is minus Eg. Eg is, so minus 1.0 by 2 kt. I mean exponential A by exponential B is A minus B. So I can write plus 1.2 by 2 kt. So the answer will be exponential of 0.2 by 2 times of 0.026. So this is 0.1. This is 10 by 123 into 3. Sorry, so this is 100 by 26. Exponential of this will be the answer. So let me. So is it 46? I mean, I don't know. This is what you have done, right? Okay, so yeah. So option D will be the correct answer. Okay, so there is one more concept of effective mass. I mean, effective mass has already been taught in the previous class, but there is one more thing that you should also know. So this is regarding the intrinsic Fermi level. First of all, I'm talking about intrinsic Fermi level as of now. Intrinsic means EI I'm talking about. So first of all, I mean, we already have these formulas. So N is nothing but NC exponential of minus EC minus EF4 KT. P is NV exponential of EV minus EF over KT plus, yes. And those NI formulas, I'm not writing it again. So what we have is for an intrinsic semiconductor, if I say, we know that N is equals to P is equals to Ni. This is what we have already established. So can I write this is equals to Ni, right? And this is also equals to Ni, right? Any doubts still here?
No.
Oh yeah, so I'll just equate both of them. So what I'm coming out is with NC. Okay, let me simplify and write it directly. So exponential term में we have minus EC, sorry, plus EF since it will come in the divide, so it will be, okay, first of all I'm talking about intrinsic Fermi level. So I can replace EI by EI also. So let me do that. So it is minus EC plus EI, and then again plus EI minus EV will be there because it is in divide. So in the numerator it will change, and this will be nothing but NV over NC. So what I can write is 2 EI minus EC minus EV. I hope I'm not doing anything wrong. This will come out to be ln NV over NC. So what I can write here is EI is nothing but, if it is, if it goes here, it will be EC plus EV by 2 plus KT by 2 ln NV over NC. Any doubts in this? I mean, this is just a calculation, so I've taken this from here to here, nothing else. Any doubts?
No, you can
Yeah,
continue.
so EC plus EV by 2 will be nothing but, okay, let me give you idea. This is EC, sorry,
EC minus EI.
EC plus EV by 2 will be EI, you are
Yes.
saying? EI? No, no, it cannot be. Okay, so EC plus EV by 2, I mean, how to give you
EF.
idea?
If it is equal,
Yeah, it will be in the mid gap, right? E mid, I'm saying. So EC plus EV, if I do, so that will be twice of the in between, and by 2 will be the mid. I mean, let's say this is point 0.5 and this is 0.1. So this plus this by 2 will be 0.3, right? E mid. This is what I'm trying to say. Is there any doubt? Please let me know if
No,
you,
sir.
yeah, okay. So EI is E mid plus this thing. This thing is KT by 2 ln NV over NC. So now NV or NC, we also have a relation. So not deriving it. So NC NV, I mean, you will see this. This is the relation that it is 2 pi mn star KT over h square this was 3 by 2. Similarly, NV has also a relation 2 pi mp star. So the only difference is the effective mass, rest everything is same. So if I try to keep this here, NC and NV in terms of effective mass, so what we get is EI is nothing but E mid plus. So since this power is 3 by 2, so 3 by 2 will come out, so it will be 3 KT by 4, and NV is above, so it will be ln MP star over MN star. Please let me know if you have any doubt in this last thing that I have written. So
No
yes,
doubt.
okay, no doubt. Yeah, so that is great. So I mean, we are covering this intrinsic. So you see, if electron effective mass is equal to that of proton, so what will be EI? If MP is equals to Ni, then what will be EI?
E mid when LAN
Yes,
0,
yes,
LAN 1 is 0.
yes, exactly. So when MP is equals to Mn, so it will be ln1 and ln1 is 0. So if MP is equals to Mn, then EI is always at the center, right? This is what we always study, I mean, that EI is always at the center. But what if this MPN is greater than, sorry, this MP is greater than that of Mn? So will it be above the center or below the center?
Below?
MP is greater than that of Mn. So will it be above or below? MP is greater than Mn. So this thing is positive. So it will be,
When that term will come to be positive, so
yes,
greater than mid.
yes.
Above.
Yes. Any doubt in above? I mean, who said below? Is there any doubt in this?
No, no, got it.
Okay, okay,
No.
yeah. Fine then. So similarly, if this is less, then it will be below, right? Below from the center. I hope it is clear. So if it is clear, please let me know the answer to this. I mean, I guess the question is very easy from what I have taught, but yeah, it is not. I mean, this is very easy. What is taking time?
Option A.
Option A. Okay. Anyone else? Any other
Option
guesses?
A.
Okay. So everyone is agreeing with option A.
Yes.
Okay. So that is it. I mean, yeah, this is the answer. So if we have the Fermi level equidistance from conduction to valence band only if the effective mass of electron is greater than is equal to that of effective mass of hole. So if we have effective mass greater than that of hole, so what will happen? It will go slightly below. If we have electron mass greater than or less than that of hole, then it will go slightly above and does not depend. So this is not even correct. So option A is the correct answer to this. I hope this is clear. I mean, this is quite straightforward. So since I've done that numerical, sorry, I mean the derivation, let me give you a very quick question. Please do not take time. This is very easy. So let's say we have a semiconductor in which the effective mass of electron is 1.4 times of m naught. M naught is the absolute mass, that is 9.1 blah blah blah. And MP is zero point 0.8 times of m naught, right? Any doubts here?
No.
So the temperature, let's say I'm taking 400 Kelvin. So what you need to calculate is you need to calculate the position of intrinsic Fermi level EI with respect to the center. Are you able to get the question? Please let me know if the question is clear.
Yes, it will be below from the center as m of n is greater than m of p.
Yes. So how much below is the question? Yeah, that is correct. It will be below.
So EI minus E mid is equal to 3 kT divided by 4.
So you need to apply 3 kT. I mean, you need to read the values. Okay, let me do it. No problem. So EI is equals to E mid plus 3 by 4 kT and ln. So it will be 0.8 by 1.4. So we need to find out EI minus E mid. So it will be, since it will be slightly below, so it will be EI minus E mid. So it will be something negative. Sure. So 3 by 4 K is, I've just said it is 8.5, I guess. 10 is for minus 5. No, so 8.6 or 5, something like that. T is 400 Kelvin I've given. And this ln thing is 8 by 14 or 4 by 7. So this is negative. So that is why this whole term will come out to be negative. So this is minus 3 for the 4, so 4 by 10, 8, 24. Okay, I need to use calculator for this. I cannot do it manually. 4 divided by 7 ln of this multiplied by 8 1. So I'm getting minus 14.4 milli electron volt, or exactly I'll write 0.0144 electron volt. I hope you all are also getting the same.
Yeah, correct, correct.
Yeah.
4438.
So you see, I mean, we need to keep a lot of things in mind that the effective mass. So in general, in any numerical, if nothing is given, the effective mass is always equal. So that is why we consider EI in the middle by default. These are all on to the question. Yeah, so this is one I guess we can do. And then we can wrap up. So we have a silicon sample which is doped with N type. So ND is 10 raised per 18. It has a resistance of 10 ohms. The sample has a area also given 10 raised per minus 6 centimeter square and a length of 10 micron. So 10 micron is 10 raised per minus 3 centimeter. You need to determine the percentage of dopants participating in conduction. So are you able to understand the question? What is it asking? Any guesses? Anyone? What are the dopants that participates in conduction? First of all, let me know this. What can participate in conduction? Any idea? I mean, any guesses? So the only thing that can take part in conduction is the free electron, right?
Yes.
And these are the impurities. So it is asking the percentage of dopant. So it is asking out of these ND how much percentage is calculating or participating in conduction. So this is what we need to calculate. So we have R, A, L, ND given. So any idea what how can we calculate N?
Yeah, from we have to find resistivity, then there we
Yes.
find conductivity.
Yeah, that
Then
is good. Yes, 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 yes. Nice. So resistivity is, I mean, the formula is quickly
R is
tell.
equal to rho L by A. So
Yes, exactly. So we have everything. We can calculate rho from here. So let's do that. R is 10, A is minus 6, and what we are L is 10 minus 3. So this will be minus 3 minus 2. So conductivity will be 1 upon that. So that will be 100, right? And it is nothing but NQ mu. I guess everything is given, no? Mu is also given. So 100 is n 0.6 10 minus 90. Mu is 800. So n we can now calculate. This is 10 is power 19 by 1.6 times 8. I hope I'm not doing any calculation mistake. So what we need to calculate is n by nd ka percentage. So n is,
7.812 into 10 power 17 for like for n.
yeah, what is the value? 7.
7.81 into 10 power 17.
Okay. And then nd is given, right? Nd is 10 is per 18. So if we want to convert in percent, we write 100%. So it will be 17, 10, 10, 0. So it will be 78.1%, right? I mean, I'm not sure about this calculation. I mean, is there any option? There is any option. So I guess the calculation is correct. So 78.1% part is taken into conduction. Any doubts, anyone?
Yeah, got it, got it.
Yeah, so I mean, these are all the basics for this particular lecture, that this is how the concentration we need to calculate. These are the Fermi level differences. So there can be many numerical opportunities from this particular topic. So now if you can imagine that how a Fermi level is going closer to the conduction band if we are doping it with N, or how a Fermi level is going close to the valence band if we are doping it with the holes. So if you have this like basic physical idea, that will be great in the further lecture, because in the further lectures we'll be dealing with some of the devices. I guess the next lecture we have PN junction, yes. So we'll be taking two different types of semiconductor and joining them together, and we'll be see what is the effect of band diagram and all that. So please go through it again. If there is any doubt, you can mail me anytime again. And yeah, you will find this lecture on YouTube also. And please also try to cover the course content that has been taught. That will make it very easier for you to understand all these problems. So if there is no doubt, then we can sum up this session.
Yeah. Thank you, Anant.
Yeah, yeah,
Thank you.
yeah,
Thanks a lot.
yeah. So thank you everyone. Bye bye. We'll meet next week at the same time.